Welcome to this video on Le Chatelier's principle. This concept is a cornerstone in chemistry, enabling us to predict and manipulate the behavior of systems at equilibrium. Over the next slides, we'll explore the intricacies of this principle, its applications, and its importance in various fields. Le Chatelier's principle explains how a system in equilibrium responds to external changes. When a stress such as temperature, pressure, or concentration is applied, the system shifts in a way that counteracts the disturbance, striving to re-establish equilibrium. It's a dynamic and fundamental framework in chemistry. At chemical equilibrium, the forward and reverse reaction rates are equal, creating a dynamic state where concentrations of reactants and products remain constant over time. This balance can be disrupted by external changes, but Le Chatelier's principle helps us understand how the system adjusts to restore equilibrium. That affect equilibrium. There are three main factors that affect equilibrium. Temperature. Changing the temperature can shift equilibrium towards the endothermic or exothermic direction, depending on whether heat is added or removed. Pressure. For reactions involving gases, altering the pressure shifts equilibrium towards the side with fewer or more gas molecules, depending on the change. Concentration. Adding more reactants or products forces the system to adjust, consuming the excess and restoring balance. Le Chatelier's principle states that if a change is applied to a system at equilibrium, the system shifts to minimize that change. It acts like a chemical reflex, striving to counteract disruptions and stabilize the reaction environment. Let's examine how the principle works in practice. Temperature changes. Heating an endothermic reaction drives it towards product formation, while cooling favors reactant formation in an exothermic reaction. Pressure changes. For gaseous reactions, increasing pressure favors the side with fewer gas molecules. Concentration changes. Adding reactants shifts equilibrium to produce more products and vice versa. The principle has three practical uses. Predicting changes. We can anticipate how equilibrium shifts in response to changes. Optimizing processes. Industrial reactions can be designed to maximize product yield. Controlling reactions. By adjusting conditions, we can achieve desired outcomes in chemical systems. Le Chatelier's principle is vital in various fields. In chemical engineering, it helps optimize processes like ammonia synthesis in the Haber process. In environmental chemistry, it aids in predicting pollution impacts. In biochemistry, it helps understand how reactions occur in living organisms under changing conditions. In summary, Le Chatelier's principle is a powerful tool for understanding and controlling equilibrium systems. Its applications span from industrial processes to environmental